All right, let's talk about this lab. It's about Ohm's law, current, resistance. And so first we need to refresh what Ohm's law is about. If you have a bulb, resistor, any device, and you connect it to a power supply, a battery, and then you measure voltage across it, and voltage is not potential. Voltage by definition equals to magnitude of potential difference. And if you insert an ammeter and measure current, then you can relate these variables. Clearly, when voltage is zero, there should be no current. And if you apply voltage, electrons start traveling through this circuit, including the resistor, and electric current is not zero anymore. And you can measure different values of current at different values of voltage. And then you say, there's a relationship. You write this law and you say, that's the Ohm's law, and that's wrong. This is not the Ohm's law. This is a definition of this new physical quantity that has a name, a resistance of this device. The Ohm's law says that for certain materials, mostly metals, under certain circumstances, mostly when temperature remains, well, constant or close to constant, this new variable remains constant. The resistance does not depend on voltage or current. But another representation of this statement is that the graph for the voltage as a function of current or current as a function of voltage should be linear, something like this, with a constant slope. And this slope represents resistance equals the resistance for one graph, or 1 over R for another graph. And the Ohm's law only says that for metals and constant temperatures, the resistance remains constant. But that's not always the case. There are materials for which this relationship is not linear. That material doesn't belong to ohmic materials, doesn't obey the Ohm's law. So it's very important to remember the meaning of this expression. That's a definition of resistance. Now, what do we have in this lab? Well, you've got the circuit, and what kind of a circuit actually is it? A simple circuit when you've got a device, let's say a resistor. You connect it to a power supply through the ammeter, and measure voltage using a voltmeter. That's your circuit. And in this situation, this is the device. You need to ignore this value because in reality it's not exactly 120 and you actually have to measure it. So power supply, voltmeter, ammeter. Just pay attention to units. And now you take data and you get something like this. Well, first we need to answer a question about how to measure voltage and current. The terminology is an important part of a language. We're measuring voltage between 2 points or across a device, and we are measuring electric current through the device. Across and through, different terms have different meanings. And of course, naturally, this is our schematic for this experiment. The device, the power supply, and 2 meters. And after watching the video, you'll get a nice set of data and you'll get a graph. Now, technically, you should have checked different fits. Doesn't really fit. The meaning of the fit is to find a curve, a line that kind of touches all the points with the least inaccuracy, with the best accuracy. And this is the measure of inaccuracy. We want this number to be very small as possible. And for that we could use either proportional, because that's what Ohm's law is about, that's what we expect, or just linear. They both are linear, you remember. But this gives slightly better accuracy with these data. Some students may have different, it doesn't matter. The y-intercept is small, either answer is good. And from the slope, because you see the linear dependence, the slope is constant, hence Ohm's law can be applied, works. So for this graph, for the voltage as a function of current, the slope not just represents, equals resistance, and your slope comes from the fit and you get your number. You just need to pay attention to units. Well, first of all, this unit is not volts per milliamps, milli, mega, pico. Those prefixes do not change the unit. They affect the value. So the unit is volt or amp or ohms. Now you're moving to a different device. You're taking more data and you see something is not really linear. If you check the inaccuracy for the linear fit, it's about 0.7. So if we try different, .567, 0.188, 0.2. So this one is the best. So this is the best fit for the experimental data for the incandescent bulb. Is it linear? No. What equation do you see? This. But in this equation, you have to replace these generic variables x and y with the actual variables. So the equation for this experimental line is V equals 0.000125 times current squared plus 0.01646 times current plus, well, negative 2.4 This measured in volts, and this measured in milliamps. That's the equation. This answers this question. And what are the units of the slope? Well, first of all, the slope to the line always can be found as rise over run. So it's going to be delta V or delta I. So in units, it's going to be volts over amps or ohms again. The unit doesn't depend on the line. The unit depends on the units of your axes. Now, does the slope remain constant? No, because it's not a linear relationship. Here, the slope is not as steep as here, so it changes. But what does it mean? Well, we could use a certain analogy. If we measure a position as a function of time and we get a quadratic function, we would say slope is equal to velocity, technically instantaneous velocity. So we could say here slope is equal to kind of an instantaneous resistance. This is a good analogy, but it's not exactly accurate, because if I'm calculating this slope, again, it has to be equal to rise over run. And if I calculate velocity, it is also rise over run. But this equation is a definition of velocity. And this equation is a definition of nothing. The definition of resistance is V over I, no deltas. So this slope has no meaning. There is a different slope that has certain meaning. And I could ask a question: what is the resistance when voltage current equal to these values? Well, you would say, okay, it has to be equal to V over I. What is V over I? That's the slope of this line, which begins at the origin. That's what V over I is. And now I can calculate resistance here, different V, different I, different resistance. And this value will be equal to this slope. So we can see that slope gradually increasing, which means the resistance is increasing. But that's a different slope, not the slope of tangential line. Well, but this is the most important statement from this experiment. This is not ohmic situation. The resistance is not constant. This device, the incandescent bulb, does not obey the Ohm's law. Well, a couple of more things here. So the slope is not constant, and not sure why we call it analysis. Everything else was analysis. So you just continue reasoning, and this part, the last part about the incandescent bulb, is the most interesting. So some students may even don't know how the incandescent bulb looks like. It has a filament inside, and when you just take the bulb out of package, this filament usually is rather straight. But if you use this bulb for a long period of time, you can see it becomes like a saggy, well, because it wears out. And when it's hot, gravity pulls on it, it makes it longer, it makes it thinner, so it might acquire some kinks. And at a certain point, sometimes when you turn it on, close the switch that connects it to a power supply, 120 volts, it breaks. Why does it break? Well, the rush of electrons basically melts it somewhere at one place, maybe sometimes two places. And this is similar to being killed by lightning. The rush of electrons damages tissue of your heart or brain. And the question here is, why? If it breaks when we turn it on, not when it is already bright and hot. Well, we need to address this by relating voltage, current, and the resistance inside this bulb. So the voltage is fixed by the power supply. That means the electric current will be inversely proportional to the resistance. And the filament is made of material for which resistance increases with temperature. So when temperature goes up, the resistance of the filament also increases. That means electric current through the filament decreases. If the bulb is destined to break, it should happen at the highest value of electric current. And the highest value is when the bulb is the coldest. And the coldest is when we just turn it on. If it does not break when it turns on, electric current decreases eventually, so there is no reason to break it after. So if it breaks, it should break at the initial instant when the current is the highest. Well, this is all with this lamp, but for curious people, I want to explain a simple model for the Ohm's law. If you got a piece of wire, you've got electrons and atoms inside, and if you applying certain voltage across this wire, every single electron starts experiencing force. Why? Well, because in the wire, non-zero voltage creates non-zero electric field, and if this is the length of this wire, electric field strength will be equal to voltage over length, and because of that there will be Coulomb's force acting on each electron. The magnitude of this force is magnitude of elementary charge times electric field. So as we know from the Newton's second law, if only one force would be acting, acceleration would not be equal to zero. Electrons would be speeding up, technically up to infinitely high speeds. That's not the case. Electrons actually traveling very slowly, about 1 millimeter per second. So on average, they travel with a constant speed, which means acceleration must be equal to zero, which means there has to be force opposing the Coulomb's force. And that is because electrons bounce back off the atoms. So this force of a kind of a resistance is proportional to the speed of the electrons. The faster they travel, the more bouncing is happening. So we could write a simple model with some coefficient for the magnitude of this force. This is the speed of the electrons. And the Newton's law says mass times zero acceleration should be equal to Coulomb's force minus the magnitude of force of resistance. Now I want to point at the fact that this letter V represents speed and this letter V represents potential and delta V represents voltage, so many V's, don't confuse them. All right, so now what do we do? Now I rewrite this equation and I drop all vertical bars. I assume all variables are positive. So if we take a look at one electron traveling through this wire, the speed will be equal to distance over time to travel, and it will be related to the magnitude of a charge times voltage divided by distance. However, now we can employ a definition of electric current. Electric current will be equal to, by definition, charge traveling through this wire in that time. And to calculate charge, well, we need to multiply the elementary charge times the number of electrons. And the number of electrons should be equal to the density of the electrons times the volume, and the volume will be equal to length times area. So I can now continue this charge density length area times 1 over T. Charge density length area times charge voltage over length over beta over length again. So what does it give me? Charge squared density of the electrons LLL1L beta and voltage. What we see now is an equation that relates electric current traveling through a device and the voltage applied to it. So we could say, let's call this combination of variables the conductivity, 1 over R, E squared N A L beta. So this variable R will represent the resistance, and it's going to be length over area times this coefficient divided by density of the electrons, electron squared. We could say, let's call it resistivity, and we get a standard expression for a resistance of a wire. But well, we also see if this coefficient beta remains constant, then we get the Ohm's law. The resistance also remains constant. However, this coefficient tells us what should happen if we start heating up a wire. When we heat it up, and these lines represent some heat. When we heat it up, atoms and electrons start moving faster, so more collisions, more resistance. Temperature goes up, this coefficient should go up, the resistivity should go up, the resistance should go up, at least for most common, most natural metals. Done.